is Japan Airlines Flight 123. Oh, sorry. What does MDT abbreviate? MDT is non-destructive testing. So it's a way of identifying potential failures in parts without actually damaging the original component. So I wanted to give you guys a quick run through on this. So Japan Airlines Flight 123 in August 1985. So the flight left, I'm going to butcher this, but Haneda Airport on a 1-hour flight to Osaka. It was a 747. It's completely booked up with 520 people on board. It was a holiday time in Japan, so lots of families traveling. Basically what happened was when the aircraft hit 24,000 feet, there was a distress call made by the pilots, and the plane descended to 10,000 feet. The reason for that call was there was a loud bang, there was a loss of air pressure within the cabin, and then there was a reduction in flight controls. So during the investigation, they determined there were 3 main contributing factors to the crash. One, the aircraft had been involved in a tail strike 7 years before the accident. What a tail strike is when you're either taking off or landing. If the tail hits the runway, that's classed as a tail strike. Many aircraft have tail strike indicators these days, but in 1985 they wouldn't have had that. But the resulting damage from that tail strike was repaired, but it wasn't fully in accordance with Boeing's recommendation. And I've got a graphic of what the difference was. So essentially, the area damaged was what's called a bulkhead, which is a big sheet of steel at the back of the cabin of the aircraft, separating the cabin and the tail. So cracks began to propagate within that repair on the bulkhead between the rows of rivets. It was after about 12,318 cycles since the repair. During the rapid decompression, several hydraulic lines were severed and the vertical stabilizer was ejected from the aircraft. So basically, pilots had very little control, and it was actually a miracle that they managed to keep the aircraft in flight for the 45 minutes. The incident was a result of several factors, but an NDT inspection would have identified the fatigue prior to the catastrophic failure. So just on this graph here, this illustration here, guys, the top one here is what Boeing said to do for the repair. So it was 3 rows of rivets with reconnecting the 2 sides of the bulkhead, the top and bottom, and a splice plate to essentially get this to spread the stress between the 2 sections of bulkhead. When the repair was actually carried out, it was 2 individual splice plates, one connecting a row of rivets essentially just to the splice plate with a gap in between, and then one splice plate, and then to the 2 sides of the bulkhead. So essentially, all the stress on the component was on the right-hand side of the illustration here, whereas the cracks and failure were propagating between here and here. Now, if we were conducting NDT on this, so at some stage during those 12,000 cycles, we would have seen the initial stress and cracks start beginning to propagate between the 2 points, and it may have actually identified the issue before it became fatal. So any questions on that? And if not, I'll just keep going. I see a question coming in, guys, so I'll just give it a second. Yeah, so essentially, the people liable for, the question was who was liable for the accident, and was it aircraft maintenance? Essentially, it was the 3 factors. It was the initial repair conducted on the aircraft that wasn't in accordance with Boeing's issued repair, and I'll go back here and show you. The cracks began to propagate, but there wasn't a failure analysis or non-destructive testing. Sorry, I meant to say. There wasn't a non-destructive testing process mapped out for the repair. When Boeing actually did an analysis on the repair conducted, they calculated that it would become unsafe after 11,000 cycles, based on the repair data that they received from the MRO that conducted the repair. So essentially, it boiled down to the repair being done incorrectly, but then there was no follow-up plan to ensure that there was no propagation after the fatigue should have been climbing on the part.
Would that be the airlines or the...
Well, realistically, it's the MRO's responsibility, Rob. It's whoever did the actual repair. If the repair was done by the airline, it'll be the airline's responsibility. But one thing to note, actually, for everyone here is with aviation, it's not like any other industry, really. If I was to install one bolt or one rivet on that repair, I'd have to sign a job card saying I installed that with my personal stamp identifying myself. So essentially, they would have boiled it down to the exact mechanic that did the repair, or the technician in the MRO, rather than just saying it's the airline or just saying it's Boeing. In this case, Boeing were on side. I didn't want to use a more recent Boeing learning, I suppose, for any of these examples because it's still so topical, but it wasn't Boeing's fault. It was the MRO or whoever conducted the repair that was in fault in this one.
Sure. Would not want to be that repair mechanic.
No. You never want your name popping up at the wrong time. Look, moving on anyway, guys. And that's just nothing else. APUs. So this is where we start basically looking at engines and motors within the aircraft. An APU is an auxiliary power unit. When you're sitting on an aircraft on ground and you hear a loud humming coming from the back of the aircraft, the lights are on and the air conditioning's on, it's an APU that's generating that power. What it does is it's essentially a small miniaturized engine with turbine sections and compressor sections running with a generator. So sorry, this is roughly where your engine is. This is your generator at the front. And basically, when you're on ground, it'll run. Some countries actually mandate that they have to be operated for the duration of flight. Some will turn it off before they take off. That's all very regional specific, but in this case, like, we're just talking through it, most people will just generally use it on ground before they power on the engines. And then depending on where they are, they'll usually use the APU power and air pressure to start the engines. So the APU is an on-condition component, and the on-condition part of that sentence is a important one to remember. Basically, we've discussed on the airframes that they are set intervals based on calendar. On the landing gear, it's calendar or cyclical. With regards to anything that's on condition, it basically means if it's not broke, we don't fix it. So we will only remove an APU if there's an indication to tell us it's not functioning correctly. So the APU is an on-condition component that will require repair due to performance deterioration or fault. Depending on the manufacturer of the APU, the required work will have a different name. So a repair, restoration, or overhaul. And the OEM will generally provide the instructions in a maintenance manual or planning guide. And what that is, a maintenance manual or planning guide is basically a book that says in order to restore, if your issue is the temperature of the exhaust gases, you go into these two modules, you overhaul them, and that'll correct your issue. So it's basically a cheat sheet for work scoping an APU. Where was I? So the work scope will define the level of work required to each section of the APU in order to restore its performance and serviceability. And while the APU may contain LLPs, so some models have had their life limits removed, it's rarely a reason for removal on APUs, as performance tends to be an issue before life restriction. So when we say performance, what we're talking about there is the operational temperatures,
Хуйня, блядь.
the power output, or with APUs you can get what's called a stall a lot of the time, where it'll just essentially stop functioning mid